Alright, in this video we're going to look at two examples, a car going around a flat curve and a car going around a banked curve. Now for the car on a flat curve example, we are using this formula right here. So the maximum speed that you can go around the curve is the square root of the coefficient of static friction times gravity times the radius of the curve. So in this problem, coefficient of static friction is 0.9, gravity is 9.8 as usual, and the radius of the curve is 30 meters. So the first thing we do is plug into that formula 0.9, 9.8, and 30. So I did that up here in Desmos, 0.9, 9.8, 30. Multiply those numbers together, take the square root, and we get a value of 16.266 meters per second. So everything in here is in standard units, so the answer should come out in meters per second. The question does ask to convert your answer to miles per hour, and 1 mile per hour is 0.45 meters per second. So if I divide by 0.5 meters per second, we get an answer of 36 miles per hour. So you can go up to 36 miles per hour around a curve like this before the tires start to slide. Now for the next example, we're on a banked racetrack, and the formula for the speed that you can go on a banked road, a banked curve, is a lot more complicated, and it depends on the angle of the bankment. So we're using this formula now for this problem to get the max speed. G and R are as they were before, but now we have to plug in the angle into this formula as well. So we have kind of complicated calculator work to do. I plugged everything in here. So in this example, 9.8, 305 for the radius of the curve, and then 31 degrees. Remember, in Desmos it assumes you're putting the angle in radians, so that's what the pi over 180 does. So it converts from 31 degrees to whatever that is in radians. But I take the sine of that angle plus 0.9 times the cosine, and then divide by the cosine minus 0.9 times the sine. That's what the formula is telling me to do. Sine plus 0.9 cosine, cosine minus 0.9 sine. So all of that put together in this formula gives an answer of 98.8 meters per second. And again, we convert that into miles per hour by dividing by 0.45, and you get a 220 miles per hour for that answer. Also with this, since this is such a complicated calculation, every time if you had similar problems, you wouldn't want to write it all out again. So what I did was set up a spreadsheet that will do this for us. And so you can plug in G, R, and the coefficient of static friction. So right now I have the numbers in here for the first example, and that was on a flat curve, so the angle was 0 degrees, and Vmax was 16 meters per second, or 36 miles per hour. In the second problem, we're changing this to 305, and this number to, well, then that is staying the same, 0.9. But then we're scrolling down to 31, and then we see 99 meters per second and 221 miles per hour. You'll notice I got 220 here and 221 there. I'm sure that's a rounding thing with how many sig figs I kept in the conversion for meters per second to miles per hour. But that's not really critical in this. If I was careful about the sig figs, they should come out to the same answer. Alright, so this spreadsheet will tell you what the maximum speed would be at any angle that you plug in along this column. And then it also shows you on the graph, when the angle is 31 degrees, the maximum speed is up here over 200 miles per hour.